Thank you. Yeah, it's a pleasure to be here at this conference, and thanks to the organizers for scheduling this. So today I'm going to talk about something slightly different from what has been described in the previous few talks in this session. I'll be talking about Green's functions for a system of random resistance networks. This was a problem that I considered based on some questions that we had in stress transmission in disordered solids, and we had some very similar physics appearing there. So we decided to study a simple problem of conductance in random media, and this is done in collaboration with a master's student in IIT Kanpur and now at Stanford. So random resistant networks are basically models for the conductivity of disordered random media, which is a problem of fundamental interest in condensed matter physics. Simple tractable models that are often used are these random resistant networks that I'm going to describe in detail. Typically, there is a weak disorder regime where the current distribution is delocalized throughout the lattice because it's very ordered. There is a strong disorder regime where the current distribution collapses onto a self-similar fractal optimal path, and lots of previous studies have observed this kind of transition between a weak and a strong disorder regime. But while the critical exponents of these regimes have been explored in detail and the scaling properties have been analyzed in detail, an analytical toolbox to analyze such disordered networks and to understand exact Green's functions in a non-perturbative manner have not been developed, which is what we try to do in this work. So I will try to describe that. So there's a lot of previous work, but I will just show you one basically done in 2005, where you have a square lattice with random resistances at every bond, and you basically put some current from here and output the current from there. And if the resistances are very ordered, there is not much disorder in the system, then the current flows basically through the entire lattice. But as you increase the amount of disorder in the system, or you tune the disorder in the system, this is basically increasing disorder, then the current basically finds an optimal path to travel, and it converges onto that optimal path. And lots of scaling exponents have been known for this kind of transition, and these are not classifiable within known critical exponents. So something like 1.22 and some strange critical exponents emerge, and there are some understandings of the different length scales in such a problem, but we tried to understand it using an exact Green's function approach. So what people use usually is an exponential distribution of disorder. Basically, the distributions of the resistances are drawn from an exponential distribution where x is a uniformly distributed random variable. You can conveniently represent the distribution in terms of this 1 minus zeta inverse function, and you can compute the distribution of zeta, which is basically given by this distribution. So as you increase the disorder, basically A is the tuning of the disorder. You start with here we are looking at periodic boundary conditions. So you start with the current coming into the center of the lattice, and you take out the current from the edge of the lattice. So when A is small, the current basically gets delocalized, and when you increase the disorder, it starts to follow this optimal path and sort of it converges onto this optimal path. So what we can do is calculate the steady state solution, basically solve Kirchhoff's laws. In this vector notation, what you can do is basically calculate the decorated Laplacian matrix of this square lattice and just invert the Laplacian matrix, and you should be able to get the solution to this problem. So how do you first start to input disorder into such a system? Well, you start with the Laplacian of the unperturbed system, and you introduce some disorder into the elements of the bonds. And you can then do an expansion of the potential at every site in terms of this disorder. So this is a disorder perturbation expansion, and you can then compute the potentials in terms of this disordered Laplacian, which basically gives you a Dyson series, and you can write down the Green's function, which is the inverse of this Laplacian matrix, in terms of the perturbation and in terms of the unperturbed Green's functions. So this is a technique that sort of is standard, and you can do that, and you can actually compute this disorder perturbation expansion, and you see that at small disorders, the perturbation expansion converges really well. But so this is the solution from the first order of the perturbation expansion, this is solution of the second order, and these numbers are very, very tiny. This is 10 to the minus 1, 10 to the minus 5, and at small disorder, it converges very well. But what happens at large disorder? Well, so we decided to look at the problem at large disorders and try to come up with an exact Green's function technique for this. So what you can do is write down the Laplacian in terms of these outer products of bond variables, because every bond has a contribution to the Laplacian. So you write it as a summation of these outer products, and this is known as a dyadic summation. So then you can also write the perturbation at every bond in terms of this dyadic perturbation. And if you were to look at one bond disorder, so that is, if you take an unperturbed matrix that you know the inverse of, and you add a dyadic perturbation to that, then there's a famous formula known as the Sherman-Morrison formula, where you can actually write down the inverse of the perturbed matrix exactly in terms of all the known quantities already. So this was done previously in for a one bond disorder. So we decided, why don't we try to generalize such a formula and do it for multiple bonds. So we then did it recursively. So if for a single bond disorder, you can actually write down the perturbed Green's function exactly, then we can try to do it for two bonds in the system. So you start with the already known Green's function with one bond disorder, and then you add another bond disorder. So then you can sort of start L2. This represents the system with two disordered bonds. You start with the one disordered bond and add another dyadic perturbation, and you can write down the exact answer again. So then this sort of led us to a question of, can we generalize this to n bonds? And you can actually do that. You start with an arbitrary number of bond disorders where you write a recursive equation for starting with n bond disordered Laplacian. You can compute the n plus 1 bond disorder, and you can sort of write down an ansatz for what the perturbed Green's function will look like, the exact perturbed Green's function, and you can actually write down the coefficients of this perturbed Green's function exactly in terms of the coefficients of the disorder, and basically it's a supercharged version of Kramer's rule, and you can get these coefficients exactly. They get more and more complicated as you increase the number of bonds, but in principle this is a non-perturbative Green's function exactly known. So we check this at the higher disorders. You can actually put bond disorder at different points in the lattice, put one disordered bond, put two disordered bonds, three disordered bonds, and exactly you can actually compute everything at high disorder, including at like disorder of order 50 and 100 and so on, beyond where the transition occurs. And so hopefully we can generalize this to understand something non-trivial about the transition. So this is a reference where we publish this. And just to complete the story, we try to understand why not try to put such a system into the computer and ask it to learn something about Kirchhoff's laws, basically using this machine learning approach. And so this was the question we wanted to understand: can the machine learn Kirchhoff's laws, and can it actually predict when an optimal path occurs? So we just looked at the simplest fully connected feed-forward neural network, where you input the resistances and it is supposed to output the voltages for you. We already know this system for some realizations of disorder, so we just train the network using that. And what we saw is that actually, if you train it for 10 epochs, or you train it for 100 epochs, or you train it for 1,000 epochs, the fidelity, of course, gets better. It learns better, and it learns in a way that is sort of spatially understands where the input and the output is. But what we found very interesting was, as you make the machine learn something about these laws, it has this two-step relaxation profile. So initially it learns very, very quickly, and then after some time it has this plateau, and then it sort of learns in a different manner. And so this is something interesting which we would try to explore further in this simple system, but it has many interesting properties. Yeah. So thank you.
Questions?
Yeah, but that would be interesting, because then they have disorder in the lattice itself, not just on the node. So yeah, but it can be done. Yes, that we know in the large N, right? Yeah. So it would be interesting to check this. But what we have an issue with is basically generalizing these coefficients to large N. So we can do it for like 10, 15, and so on, but these expressions get much, much larger. So we wanted, hopefully, we could get some sort of asymptotic values of these coefficients, but we still haven't got that. But it would be very interesting to check this. Yeah, that's a very good idea. Yeah.
Okay, let us thank the speaker. Let us end the session. Thank you.